Okay, I think it's time to get started again. So, last time we had some introductory material. We saw a couple of motivating examples for the idea that, well, here's the main idea that'll go across all of my talks. The idea that there's some very important tasks that we might like robots to be able to solve that we can solve with surprisingly simple robots. Okay? So today I'd like to zoom in on that idea a little more and present some of my own work done with my advisor Steve Laval and one of my master's students, Mr. Jeremy Lewis, on some specific kinds of problems that fit into that same mold, but we'll talk about them in some more detail than we did last time. So here's one basic problem that turns out to be extremely important for mobile robots to be able to solve. It's this problem of localization. Right? So the question we want to answer is, well, the robot wants to answer the question, where am I? Right? So we can imagine a robot in some environment. You can see it there in sort of the classic theoretical roboticist robot view of a circle with a line showing the direction. And the robot is in some environment, and let's assume, for today, let's assume we've got a map of the environment. So we know what the world looks like, we know where all the obstacles are. Let's go even further and assume that we know all the sizes and shapes of the obstacles, right? So if you like, let's suppose we have a doubly connected edge list describing the shape of the environment that the robot is moving in. And the question is, if the robot doesn't have any idea where it is within that environment, what can we do? What kinds of strategies might we use to go from that position of total uncertainty about where we are within the environment to knowing where we are, right? This is the localization problem. I should be more specific, I suppose. I'd like to talk about global localization. So global meaning starting from this sort of complete uncertainty, right? In contrast to other methods in robotics that think about passive or think about only a local localization where we just try and not forget where we are. And I want to talk about active localization. So rather than just trying to keep track of what the robot might know, we're actually going to choose motions for the robot, right? So there's a few different varieties of localization, but in some sense we could think of this as the hardest version, right? So we don't know anything about what's going on, and now we have more responsibility than in some other approaches. We actually have to choose the movements for the robot, right? So that's the idea. The question I'd like to ask is, what kind of sensors do we need? How strong of a robot model do we need in order to make this problem solvable, right? Another way to say this, the same question is to ask, what are the information requirements for this task, right? So we've got a robot interacting with the environment. It's going to be able to collect some information by sensing things, by moving around through the environment. And I would like to know how much information is really necessary to achieve this. So I am not by any means the first person to work on this robot localization problem. In fact, there are well, zillions of papers on this robot localization problem. Here's just a few. You can tell that I made this slide sometime in the mid-2000s and haven't updated it since then. But so it's not intended to be complete, but just to give you an idea of how well studied this problem is in robotics. Right? The one common thread through, if I'm seeing correctly, every citation you see here, the common thread through all of them is this idea that these papers are looking for sufficient conditions. Right? They describe a robot model and say, look, this is enough. Right? If you have this, then you can solve the localization problem. Right? We want to go in a slightly different direction. Right? We want to make the robot simpler and simpler and simpler until finally we reach some level of bottom where, according to some measure, we've got the simplest robot that can do these kinds of things. Now, it turns out to be pretty tough to achieve that goal completely, but we can get pretty close, and I'll show you how that works. Okay, so we can think of lots of different kinds of sensors we might use to solve this problem. Maybe some range sensors, we talked about those last times, or cameras, or landmarks. We can think about odometers for measuring distances that the robot moves. Lots of different choices. I'd like to propose just one specific model here to start with. And that would be a robot that has a compass, So by compass, I mean that the robot has some sensor that can tell it its own orientation with respect to some global frame. Right? So if we tell the robot to face north, it can face north. If we tell the robot to face 10 degrees from south, then we can do that, right? So we can choose the orientation of the robot with respect to some global frame, and that global frame turns out to be very important. Right, so we can choose which direction we want to face, and face in that direction. And then we'll also imagine that the robot has a contact sensor. So we can drive forward, and we know when we hit something, and we can stop at that point, right? But that's it, right? In particular, you might be thinking that there ought to be some kind of sensor to measure where the objects are relative to the robot. We're not imagining anything like that. You might be thinking about a sensor that can measure the distance the robot is moving. Not considering anything like that, right? Really, just face the direction, and then you can drive straight ahead until you hit something, right? Question?
The radius of the sensor is limited?
The radius of what? I'm sorry. Okay, so the range of this sensor is 0. Right? So I don't see the obstacles ahead of time. I know them only when I hit them. That's it. Right? So yes, the range is extremely limited. Question?
You can only find the region of the place where the robot is. You can't say specifically what point the robot is.
That's right. So to start, we know the shape. Right? So in this case, we have a list of 1, 2, 3, 4, 5, 6, 7, 8 points in order around the polygon. But we don't know the starting location. It could be anywhere within the polygon. Did I see another question? That's it? Have I answered yours? Is that right? So the goal is, given the map, produce a series of motions for the robot such that when that series of motions is finished, we know where the robot is. Right? Okay, so what kinds of motions can we imagine doing with this kind of robot? Since we can't measure distances, we can't give it a command like drive forward 3 meters. Since we can't see the obstacles until we hit them, we can't give any commands that say, drive toward this obstacle or that one. Really, all we can do, I suppose, is pick a direction. Right? We can use our compass to do that, decide which way to go, and then just keep driving until we hit something. And that's about all we can do, all right? So the result we have here is that that in any, and I'll say it explicitly this time, in any simple polygon, turns out that we actually can solve the localization problem using this kind of sensing and movement model. And I'll show you an algorithm for actually computing the motions that do that. Right? So there's a very, very simple example here that maybe gives you a feeling for how this works out. So in this kind of environment, right, suppose the first motion we make is to drive straight up. Right? So if we do that, we still don't know exactly where we are, but we have a lot more information than when we started. Right? So in this environment, regardless of where we start, after moving up once, then we know we're somewhere along this top edge, right? We don't know where, and we're not assigning any probabilities or anything. We know we're along that top edge somewhere. Then at that point, if we turn the robot and drive to the right, then at that point, regardless of where we started, we know we'll be in that top right corner, right? Everybody buy that much at least? Right, that in this environment, those two motions can get us to a position where we know we're in the top right corner. Right, of course, this is quite a far cry from an algorithm that'll solve this problem for any kind of environment. But at least in this one, we can do it, and those two motions will get us there. Right. So now I think you see the problem. Right. We have as input a polygon that describes the environment the robot is moving in. And the output is going to be a sequence of directions, right? Go up, go left, go right, or any of those things in between, right? It doesn't need to be orthogonal. And so we want that sequence of motions as output, along with a promise that the robot will be in a known position after that's done. So generally we think of that final known position as part of the output as well, right? Okay, so how do we do it? Well, there's actually two phases that we can think about the algorithm going through. The whole idea is based on keeping track of which locations in the environment are possible locations for the robot, right? So, in the example we saw here, after one movement, we had a segment of possible locations across the top. After two movements, we had just one single point, a singleton, as a possible location, right? So we want to keep track of these. We call them information states, right? These subsets of the environment where the robot could be based on what we know about what it's done in the past. Right? So we'll actually generate this sequence in two phases, right? We start out with anywhere in the environment being a possible location for the robot, right? Turns out we can simplify it a little bit and just draw the entire boundary of the environment as a possible location, right? Anything in the interior will get mapped onto the boundary within one movement, so we can ignore the interior. So we need to do some stuff to get the set of possible points down to a finite set, right? So all these line segments that we saw, we want to get rid of all those first. Then once we've got a finite set, there's some extra stuff we can do to collapse that finite set of points down to a single final point. Okay, so that's the general outline of how the algorithm works. This kind of matches with some other papers, particularly Dudek, Romanek, and Whitesides, who inspired some of this work. So we'll call these two phases hypothesis generation, right, getting to a finite set of possibilities, and then we try to eliminate some of those. Right? Okay, so the first question is, given a world where the robot could be anywhere along the boundary of the environment, what kinds of movements can we make to get that down to a finite set? And I was actually quite proud of myself. I felt like a real computational geometer when I designed this sweep line algorithm. So here's the idea. We sweep a line from left to right across the environment. And the invariant we want to maintain is that there are only a finite number of possible locations for the robot to the left of the sweep line. And so as we move across, if the sweep line reaches a single point, that's okay. We just keep going. But if the sweep line reaches a line segment, then we can't keep going without adding a motion to our plan, right? So it actually turns out to be fairly simple, because you'll notice that whenever the sweep line reaches a line segment, we can choose a motion that collapses that line segment down to a point by choosing a motion that's parallel to the edge that holds that line segment. Right, so in this case, this is decidedly not in general position. So there's actually 1, 2, 3, 4 different segments we reach, sort of all simultaneously. Which one do we choose? We'll just pick one, right? And in this case, happily, we hit 4, but they all have the same direction, right? So we choose a motion that's parallel to those edges. Of course, there's 2 directions that are parallel to each edge, right? And basically, we want to choose the one that is in the same direction as the sweep line, right? So this first one, we can sort of go left or right. We want to go right to make sure that we're not mapping any segments back to the left of the sweep line, right? And I actually realizing now that I left out the details about how to compute these sets of possible states. Let me just mention that it's relatively easy to do. There's another sweep line algorithm in there that has a feeling sort of similar to ray shooting, but in this case it's more like a segment shooting sort of problem, right? So we can do that. I hope you won't begrudge me that exercise that I'll leave to you. Happy to talk about that offline, right? But that's the idea, right? We sweep from left to right. Anytime the sweep line hits a segment, we can generate one motion to restore the invariant, right? So in this case, we reach those segments here, generate a motion to go to the right, and then after that we know the robot is in one of these red places, and the sweep line can keep going. We reach this segment. Here's degenerate, right? We could go up or down, it doesn't matter. My code happened to choose up. And then at that point, by a very, very happy coincidence, all of the line segments are gone at that point, so we can sweep all the way across. Right? So you may get the idea that this is a very efficient algorithm for doing this. We did this whole complicated environment in 3 steps. Turns out to be perhaps slower than you might expect. Right? And it doesn't show up very well here, but the reason is that when we generate these motions to collapse one line segment, some other line segment somewhere else will be moving around, right? And in very bad cases, we can get, for example, lots of tiny pieces of possible states along each segment, right? So in practice, I've never seen anything even close to this n-cubed bound, but that's the best bound I've got. And actually, many of you are probably better qualified to improve on that bound than I am. Question?
We assume that our polygon is axis alone.
No.
So if we have a line like this, and we sweep the line, our answer is correct.
Yes. So.
We sweep a line left to right.
Yes.
We collect these segments, and after that, we assume that if we go up, we reach these points.
Right. So at each event in the sweep line algorithm, we generate one motion that is parallel to the segment that the sweep line reached. Right? So if the segment is not axis aligned, then the movement we get is not axis aligned. Right? But always moving to the right. And so everything sort of gets pushed forward, and you can show that at least eventually you run out of segments to collapse. Right? So it is correct. This example is in some ways not a perfect example because it has a ridiculous number of degeneracies. Right? If you can wait just a minute or two, I'll show an example where I've broken all those degeneracies. Okay. Any other questions I can answer so far? Okay. So this is part of our solution, right? We generate some actions as the line sweeps from left to right, maintaining the invariant that we have no line segments left of the sweep line. Once the sweep line is all the way across, then we've got no line segments at all. Right? We just have a finite set of points. Right? So here's the question. How do we get from that finite set of points down to a single known point? And well, it turns out that's a little trickier to do. But here's the basic idea. Okay, so the first thing is if we have n points, pick your 2 favorite points, right? And wrap the procedure I'm about to describe in a for loop that eliminates 1 point at a time, right? So if we can solve this problem for 2, then we can iterate it to get the whole solution down to just a single final point, right? So that's the first idea. So let's let P and Q represent the 2 points, right? So each of these are 2 possible locations that the robot could be, and we want to generate some motions so that regardless of whether we start at P or at Q, we end up in the same final location, right? So how do we do that? Well, there's 2 cases. One case is that maybe P is visible from Q, right? That doesn't happen here, but right? So we can take a look at the visibility polygon of P, and Q is not in it, right? So that's sort of bad news, right? If we have P visible from Q, or Q visible from P, then we can solve it in one step, right? Just take the direction from P to Q and we move that way, right? But in this case, since Q is not visible from P, we can identify one edge of the visibility polygon of P that corresponds to Q, right? And you might remember that I said we had a simple polygon here, right? This is precisely where the fact that there are no holes in the polygon becomes important, right? So, right, if we have a loop down here, then it's not clear whether to associate Q with this side or this side. So we identify that edge and we move parallel to it, right? So essentially, we're imagining a game of hide and seek, right? So P is chasing Q, We can't get to Q directly, so instead we move parallel to this edge here, right? So we send P, in other words, toward the vertex that hides Q from it. Right? So we get something like this, right? Now the important thing to notice here is that I've got two dots here, but there's actually only one robot, right? We just don't know which position the robot is actually residing at. So when P moves in that direction, Q moves in that direction as well, right? So again, we're updating our set of possible states, and this really is just a pair of ray shooting queries in the environment, right? Okay, so that looked nice for a moment, but gosh, it's not any better, right? So we have a new P and a new Q, and we've added one motion to our plan, but still P can't see Q, right? And the intuition here is that we iterate this process, right? Again, we identify the edge that hides Q from P, we move in that direction, and now we're in good shape, right? Now those two are visible. When P can see Q, then we move in the direction that separates them. And again, there's two. In this case, just pick whichever you like. And so finally, we get down to a final position where those 2 points meet, right? All right, but keep in mind that here we generated 3 motions for our plan. Both of them are the same motions for both points, right? So regardless of whether the robot started at P0 or Q0, after those 3 motions, it'll end up down here, right? So natural question here is to make sure that this process converges, right? To make sure that eventually P can see Q. And the basic argument is that as P, what's that? Okay, so yeah, if you have a loop, there's trouble, right? For a simple polygon with no holes, then you can argue that P visits each edge at most once. So at most n iterations to merge P with Q, right? Now I suspect, but even in the time that's passed since I worked on this, have not been able to prove. I suspect that this approach can still work when there are loops. But if somebody knows how to prove that, I'm curious to see it. Right? So that's the idea, right? We take 2 points. We can make O of n motions to merge those 2 points, right? So that reduces our set of possible states by 1, right? Then pick 2 more and generate some motions to merge those 2, and so on, right? So eventually you get only a single point, right? Okay, so how long does that take? There's more. Actually, this isn't any more bad news. We already had an n-cubed number of motions here. So the bound here turns out to be the same. So O of n cubed plus O of n cubed is O of n cubed, right? So we can solve the problem, right? And I haven't proven it here, but I hope you can start to see the intuition that this will work for any polygon, right? It's not a question of deciding whether some sequence exists to solve a particular polygon. I promise, a sequence exists to solve this polygon, and this algorithm can generate it. Right? So that's sort of good news. Let me show you what it looks like. So here is here's that environment I showed you before, and in red you can see what the algorithm is actually computing. Then in blue, just for illustration purposes, not used by the algorithm, in blue you can see a bunch of possible starting points for the robot. So you can see this is that first leftward motion that gets generated, and here they're synchronized just so we can see the steps happening one by one. And you can see actually very quickly this process is able to get down to a finite set, right? Or actually down to a single point here, right? So this works great. In particular, there's lots of these self-similarities here in the environment, and the algorithm is able to deal with those very rapidly, right? So that's a nice example. Here's an example that is, look very similar, but just applied some small, not quite random because I did it by hand, but arbitrary perturbations to each of the points. And
what's your next direction when you hit the obstacle?
The next direction when you hit the obstacle is determined by the motion sequence generated by the algorithm. Right? So the output of the algorithm is go this direction, then this direction, then this direction, and so on. Right? And the robots are just iterating through that sequence. Right? So the message here is that, I suppose not to be fooled by the apparent simplicity of how well it worked for that first environment. Right? This one is very similar. And actually, the strange thing is that one of the things that tends to make robot localization difficult in usual settings is the fact that if environments have self-similarities, that makes the problem harder because the robot has a hard time telling those things apart. Right? Here it's inverted. Right? Here I've broken all the self-similarities, and for example, if I had a range sensor, I could tell the differences between these things very easily. Right? With this kind of problem, we lose those nice bonuses we saw in the other example, where one action was doing a lot of work for us here, right? So, strangely enough, the set of environments where this localization problem is hard are the opposite of the ones where localization is hard in general. Okay. Is it clear what's happening here? Is there a question?
When you move around that line, you didn't have a gap sensor.
Oh, okay. Yeah. So in this case, I'm making a ridiculous assumption. Right? The assumption is the robot can sense its orientation. Right? So for example, I know that this wall faces exactly north to south. So if I'm standing next to it, I can say, maybe you guys know the directions and it sounds strange, but I can say face north, okay, and then I can follow it. Right? So I don't sense the wall. But I know I may be against it, I know its direction, and I can move in that same direction. Anything else I can add here? Right, so I think the impact of this kind of result is to notice that this is a very, very simple kind of sensing model. We're not collecting much information about the environment at all. In fact, it's so simple that there's not even any feedback. Right? The strategy that the robot is executing is just simple feed-forward list of actions to take. Right? There's no ifs, there's no loops in the plan, and it's still able to figure out where it is by executing those movements in order. Right?
In this example, all of us select the same direction.
Yes, that's right.
But this requires some message passing between.
Okay. So this is an important difference, right? There's one robot, only one. So there's no message passing, right? However, the robot does not know its own location. So the beginning of the video is illustrating many possible starting locations for the robots, executing in parallel. Many ghosts or spirits, showing where the robot might be. But there's only one robot. They all move in the same direction because the robot doesn't know which one is really him. Right? So they all must move in the same direction in this kind of model.
Then the robot finds its final position.
Yes.
How we can understand which is in final direction.
Okay, so along the way, the algorithm is computing these red regions, right? And we can prove that the robot's true position is always inside one of these red positions. Then when the algorithm is finished, we know that the red region is only one point, right? So when these movements are finished, regardless of the starting location, all of those map down to the same final location. Right, so we can, what's that? So we cannot determine the starting position. We only know the final position. In fact, you cannot go backwards, right? Because you don't know the distance the robot's moved in each of these directions. Does that make sense?
Which edge of the visibility polygon do you select every time?
Okay, so for this part, yeah? Yeah. So, okay. So there's two cases, right? One, which is P can see Q. That's easy, right? You don't worry about the visibility polygon. Otherwise, Q is hidden in one of these. Maybe we can call them shadow regions, right? So. In fact, the visibility polygon sort of partitions the rest of the environment into distinct regions, each of which corresponds to one of these. Well, I've heard them called spurious edges sometimes, right? An edge of the visibility polygon that is not part of the environment boundary, right? So we need to find the spurious edge that corresponds to Q. Can I say anything else about this? I'm not sure I've communicated it very well. Okay, so I hope you will at least believe that given a polygon, I can generate a sequence of motions such that after we do those motions, we know the robot knows where it is, right? We don't get to choose what the final location is in this algorithm, but it's going to be one single final location. Okay, so
But does it mean that you can choose it?
well, so. You can, sure. Okay, so yes, you can choose, but I've not mentioned that part, right? And it's true that it's not too hard once you know where you are to bounce around to get where you want to go. But
you can't go to arbitrary points, right? Because of the constraint on the fact that you have to go into.
I'm dipping into the realm of speculation at this point, but I believe you can reach an arbitrary boundary point. I think so. But the fact that you're surprised by that is making me second guess myself. Okay, so
how would I get to this midpoint of the upper edge or something like that?
Midpoint of the upper edge, I would go this way, then this way, then this way and this way, right? I mean, you have a fine level of control.
In the direction.
Yep. Okay, so let's keep going here. So we showed how to solve this problem with a compass and a contact sensor, right? So we can measure or choose a direction to face, measure with respect to a global frame, right? I emphasized that before, and we can, after facing that direction, drive until we hit something, right? We show that we can solve the problem under that model. Is that the simplest we can do? Can we make the robot any simpler and still be able to solve this problem? And so here's an alternative sort of robot model that is very, very similar to the one I just described, with one difference that turns out to be vital. So the contact sensor part we will keep, right? So once the robot is finished rotating, we let it drive forward until it hits something, right? And still no distance measurements. All of the same kinds of things apply. But the one change that rather than specifying directions with respect to a global frame, let's imagine a robot that only has some kind of angular odometry. So we can give commands, instead of saying face north, we can only say turn 15 degrees or turn 90 degrees, right? So now the measurements or the movements that we make for the robot to rotate are going to be expressed in relative terms, right? So if we ignore the possibility of errors accumulating, then we could think of those directions as being specified relative to the robot's initial orientation, for example, right? So this is very, very similar. The only thing we changed is that now we have relative angle measurements rather than absolute ones, and suddenly everything comes to a crashing halt, right? We can prove that no algorithm exists to localize the robot for these sensors. Can you see why? Or maybe not. The proof is actually simpler than you might think, especially for this whole idea of sort of no algorithm exists is a dangerous thing to say, but it turns out to be fairly easy to get in this case. So here's the idea. Suppose you do have an algorithm that solves the problem with these these models. So I give you an environment, and it goes through your algorithm, and you give me a sequence of motions to make, right? Turns out that to get from a situation where you have any point along the boundary as possible to get from there down to a point where only a single point is a possible location for the robot. For that to happen, we have to have at least one motion that is parallel to one of the edges of the environment. Right? So every correct answer has one motion, at least, that is parallel to some edge of the environment. Right? So that worked out fine, and in fact, the algorithm we showed for the slightly more powerful case used lots of these edge parallel motions. Right? But if we're thinking about this model where the directions we choose are relative to the starting orientation, if we want the algorithm to succeed, we need to make sure that the plans we generate are correct for every possible starting orientation of the robot. Right? So the set of directions that the solution your algorithm generates, the set of directions that your algorithm moves in is a finite set. Right? And the set of directions is infinite, right? So if I, as your adversary, want to break the localizing sequence you get, all I need to do is choose an orientation for the robot that doesn't line up with any of the motions you picked, right? So for every sequence of motions, there exists at least one, in fact, sort of almost all of them work this way. But there exists at least one starting orientation for the robot where none of those motions are parallel to any edges of the environment. Right? And then if that happens, we can show in a fairly straightforward way that there's going to be at least one non-trivial line segment of possible positions left after the robot's done executing that sequence. Right? So for any environment, for any motion sequence, there exists a starting orientation for the robot where that sequence fails, right? So this is kind of bad news, right? The picture here maybe illustrates it fairly well. So here's a simple environment, and for this orientation, it's fairly straightforward, right? We go up and then over. But for a different starting orientation, we get a different set of final possible locations. And right? There's just too many starting orientations for any finite sequence to have motion parallel to one edge in all of them, right?
So the statement that you're proving is actually stronger. So you're proving that for every polygon that does not exist in the algorithm. I mean, it would have been, from what you said before, you said, I would have thought maybe you showed that there exists one polygon.
Oh, yeah.
So you say no matter what the input is.
Yes. Yeah. So it's not just for nasty polygons. It's for everybody. Yeah. It's easier than it looks, right? But I guess maybe the message here is that that global measurement is actually really, really important. Right? The fact that the first model I described has enough information to specifically line its motions up with the edges in the same reference frame that you've drawn the environment in. That turns out to make all the difference here, right? Okay. Any other questions I can answer about this part? In the paper itself, the proof is very, very short. Right? There's actually not a whole lot to say about it. Right? Okay, so we've got some good news that for one simple sort of model, we can solve these kinds of problems. And we've got some bad news, right? That if we make the robot just a little bit weaker, then we're stuck, right? That we can prove it's not solvable at that point. Well, I guess another thing we might try is, all right, so we made the angular measurement a little bit weaker, right? And then that ruined things. We can't solve it at that point. But maybe if we increase the robot's linear measurement ability, then things might get a little bit better, right? So let's think about a third model where the robot has excuse me. Where the robot has an angular odometer, right? So this is the same as before, right? Relative motions, turn 90 degrees, turn 15 degrees, whatever. And now we add a linear odometer, right? So rather than just keep driving forward until you run into something, let's think about a robot that can measure distances, right? So if we want to model this carefully, let's say that the robot can attempt to move forward a given distance d, and If there's room to move forward distance d, then it actually will and stop there. If there's less than distance d ahead of it, then it'll go as far as it can and report how far it went. Right? So now we're thinking about a robot that can rotate accurately and measure the distance it's translating accurately, but one that still has this relative property of its motions. Right? We still don't have this compass that lets us get the proper orientation. So turns out if you think about this model, we have good news again. Right? If we use this model, then the robot actually can localize itself. And well, let me show you how. So the first thing that I'll ask the robot to do is, it's actually a fairly simple idea. So first thing the robot should do is drive forward, and the distance it should ask to drive forward is infinity. Right? So essentially, drive forward until you reach something. Throw that measurement away. Right? Then turn 180 degrees. Right? So suppose the robot started here. It should drive to this point, then turn around. Right? We want to make sure that we are departing from one edge of the environment. Then we drive forward as far as we can, right? And we measure this distance. Right? Then we turn 90 degrees and drive forward as far as we can again. We measure that distance. Oh, and by the way, it might be, depending on which side you end up on, that after that 90-degree turn, you hit the wall immediately. If that happens, then you turn 180 degrees, right? So we want to make this L-shaped motion, where the angle of the L is 90 degrees. We picked 90 because that makes the math work out easier. There's nothing magical about it. And so L-shaped motion, 90 degrees, and all 3 points on this L are going to be against the environment boundary. So the important thing here is, actually, there's nothing here so far that we couldn't have done with the other robot model. Right? The important thing here is that now we know the distances associated with those two. Right? Knowing those distances, it's actually fairly straightforward. Well, it took me a while to get the equation right, but once you know how to do it, then it's fairly straightforward to compute the set of all final locations that match with those two distances, right? So in the end, there's a quadratic there. So you end up getting, for example, for one triple of edges, you get two solutions here. So the blue one and the purple one are both coming from the same triple of edges. One of them is wedged higher and one of them is wedged lower. Is this clear? Okay, so that's the idea. So we ask the robot to make these three motions, getting those two measurements. Then we just loop over all triples in the environment. Sorry, n cubed again. And it's actually constant time operation to generate, if one exists, generate these two candidates. Right? So this is good news, right? So given these just a handful of motions to start out, we have already found a finite set of possible locations for the robot, right? Then from there, to get down from that finite set to a single known location, we can do something like this. It's actually the same trick as we used before. If we have a finite set of points, just pick two of them. Pick your two favorite points. So they're shown here on the left in red and green. And basically we want to plan a path that eliminates either one of those points or both of them, if possible. Right, so here's how we do this. Excuse me, just a second.
Maybe one question. In comparison to what you did before, so now the algorithm is much more complicated because it can branch, right?
Yes,
so
indeed.
Information, and then depending on this, you get this set of points, so it's not the same for all possible.
Yes, that's right. So we do have branching now, and you can express it as a decision tree. It's maybe easier to express it as with a feeling more like an online algorithm of measuring a distance and then responding to that. But indeed, the general data type of the solutions has gotten more complicated. Right? It comes directly from the fact that now there's a number coming back from the sensors, which we didn't need before. Okay, so we have 2 points, and we would like to make some motions to guarantee that after we're done with those motions, we've gotten rid of at least one of these 2 points. Right? Maybe we'll get rid of both of them. In particular, if neither one is the correct location for the robot, then they can both disappear, and that's even better. So to do this, we draw 2 copies of the environment. Right? So we choose a coordinate frame where let's put the robot at the origin facing up. Right? So this red one and this green one, we put both here. Right? So 2 possible positions for the robot. We essentially slide the environment around so that they're both in the same spot, facing the same direction. And then we draw in what the environment looks like based on that rigid body transformation. Right? So we sort of draw a robot-centric view of the world. And the interesting thing we can see is that the environment in general is going to have some partial overlap. Right? What we want to do is choose a path that crosses exactly one of those 2 boundaries. Right? So not both, because if it crossed both, then as we execute that path, we wouldn't be able to tell the difference between those 2. Right? We want to disambiguate red from green. So to do that, we've got to cross either red or green, but not both. Right? And in this case, I just chose one. That crosses just red, right? So why is that useful? Well, turns out that if the robot had started out at the red position, this plan is telling it to rotate 90 degrees and then drive forward about this far. If the robot from the red position does that, then it'll reach the boundary before it can drive that far, right? And our odometer will tell us, yes, you'd love to drive this distance, but you actually only went this smaller amount of movement, right? Right. So if that happens, if the robot gets only this far before reaching the wall, then we can eliminate the green candidate, right? And same thing, right? If we execute it from the green location, rotate 90 degrees and come down this way, the robot can go that entire distance without reaching the boundary. If that happens, then we can eliminate the red one. Right? Then there's a third possibility that neither one of those happens. So the robot may end up stopping over here, for example. And in that case, we know that neither red nor green is correct. So we eliminate them both from our set and choose 2 others. Right? So we can do these overlays to determine to generate a path that helps us make some progress. Right? So then, given this set of of possible locations for the robot, we can pick 2 of them, make just a few motions, in most cases just a few, to eliminate at least one of them, and then as we did before, we iterate that process to get rid of all of them except one. Right? Is the idea clear? Okay, so let me show you what it looks like. I need to pause it quickly here. So you can see it's already started through those initial motions. And right here, this is the result that you get from that first step, right? So it makes the L-shaped motion. And in this example, the actual robot is shown in blue. Now, this is the robot's true position, but it doesn't actually know where it is. And all of these little ghosts here are showing locations that are consistent with what the robot has done so far. Right? So as we did before, we're keeping track of which places in the environment match with what we've done already. Right? And as you can see, we get a bunch of them. Right, then the other thing that happens, once it's generated these candidates, we immediately pick 2 of them, and they're shown in red and green up here. And we generate a path that eliminates at least one of them. Everybody pay attention closely, because the process goes fairly quickly here. As you can see, most everything is eliminated after just. the only possibilities that are left are the ones that sort of match with the shape of the part of the environment that the robot's in, right? Here you're seeing that effect where self-similarity in the environment causes the robot to be confused, right? So this is the classical robot localization dilemma, where places that look similar are hard for the robot to tell apart, right? And you can see in purple and green here are the two candidates that it's trying to disambiguate at this point. And I think the purple one is actually correct, right? So you can see it kind of continues here. And after actually just a very short time, we reach a situation where we have just two candidates left. And in this case, it looks like there's actually a lot of work to do, right? You'll notice that in this particular environment, there's sort of large-scale self-similarity. So we've got a left copy of the environment and a right copy of the environment. And those two differ only in this spot right here, right? So in the left copy, this spot is open, and in the right copy, there's a wall here, right? So the algorithm sort of generates a path that drives the robot through those. So the purple dot you see there is the destination that the robot is aiming for. Right, and so actually you have to go all the way around, right? So it could be the number of steps is linear, potentially, in the complexity of the environment, and then eventually right here, right, as soon as the robot gets around this corner, it'll be able to tell the difference, right? On the purple side, it'll be able to move forward. On the green side, it will not be able to move forward, and then it gets eliminated, right? And we actually kind of delay the processing until the end of that step, but so then it's done at that point. Okay, so that's the idea. And actually, I'm running a little low on time here, so let me stop there and answer any questions you may have.
For the start of the process, you make random copies of the robots in the whole workspace?
No. There's no randomness in any of these algorithms.
I cannot understand that why these are why you have to check the path with finite other paths.
Okay, good. So that happens here, right? First step is make this L-shaped motion. Right? You know those two distances. I've omitted the equation here, but given 3 line segments and 2 distances, you can solve for the 3 points where the robot would need to touch if it traveled those distances between those 2 line segments. And it turns out that for a given triple of line segment, I don't know why I'm gesturing. There's a whiteboard here, right? So if I have 3 line segments, and I know the robot traveled distance 1 and distance 2 with a right angle between them, D1, D2. So given the coordinates of these 3 line segments and these 2 distances, I can solve for these 3 points. Right, so given the line segments and the distances, this is determined. Right? So the algorithm is first command the robot to make these movements, get these 2 distances, then 3 nested for loops over all triples of line segments, and solve for the final points. Right? And I've drawn it a bit deceptively. For a given triple, there can actually be 2 possibilities because it's a quadratic equation. Right? So after we do these and loop over all the triples, we take the solutions to all of those problems, and that becomes our finite starting set. Right? Those are the only places that match with going this distance, right angle, this distance to the boundary.
Let's say I mean that. Why there are how you check the match of this path to other places of your workspace? I mean, how you can determine that this path can be happen in other places in your workspace?
Okay, so the idea is we check the entire workspace. Right? The robot doesn't know where it is, so across the entire workspace, every triple of edges, we check. We see, is it possible to go this distance, then this distance with right angle in between? We try everything.
One point from one of the edges to from one point from the other edges, and 3 of these edges, all of the points have to be checked?
Yes. Yeah. So for I equals 1 to n, for j equals 1 to n, for k equals 1 to n. Try that triple, right? Solve for the final position if the robot had moved from this one, from segment I to segment j to segment k. Right?
This can be computing all one.
Yeah. So that the final position given the 3 segments is O of 1. It's just a quadratic equation. Okay. Any other questions I can answer?
So if there's imprecision and then your measurements, do you get any results? Or?
Yes. Stay tuned. Come back next time. So indeed, David makes an outstanding and actually fairly obvious point that in addition to being very simple, these movement models are ridiculous. Right? They assume that the robot can make all these motions very precisely. If I may, let me, and I'll stop in just a second. But since David asked, let's see. Yes, so something like this algorithm can work, and you're missing the video here. So it's a very natural question. What happens if there's some imprecision? So the robot we used to test this out was Roomba vacuum cleaner, right? And the algorithm did have to change. So the probabilities, we used probabilities to deal with the fact that there were some uncertainties. And next time I'll present more of a worst case flavor for solving these kinds of problems. And it's very slow because, research robots are very slow, so I'll fast forward here. The end result is that regardless of its starting position, with high probability, I have to add for this part, the robot will end up in that top right corner. And so a better answer than stay tuned is, yeah, kind of. Okay, any other questions? So thanks very much. I guess it's time for lunch, right?